Hi, my name is Mike Zandy. I'm going to be talking about some research that my teammate Anthony Blanton and I did on BlackBerry Silence's applied research team on detecting and preventing stack pivots on Linux using BPF. I'm going to cover some background intro information, talk about our proof of concept design, some testing and benchmarking we did, and then wrap up with some final thoughts. As far as scope, we're only going to be talking about Linux AMD64 architecture systems, and we're only trying to protect userland, not the kernel. Motivation is, can we use BPF to stop exploits as they happen instead of just alerting? And I want to give a shout out to Tetragon for essentially answering yes and taking a more general approach than we did. I haven't run it myself, but having looked at the code, it's pretty impressive. So shout out to everyone who's worked on it. Also, the closest thing I could find in prior existing research to the approach that we wound up taking was used in RopGuard, research from about 10 years ago, but that only focused on Windows. However, it's been implemented in Windows Defender nowadays, so shout out to that research as well. Reading between the lines, the goal is we want something that we can apply on a system as it is without having to rebuild software. So what's a stack pivot? Well, I'm going to assume that we're generally familiar with the stack. It's a very popular target to get code execution if you have memory corruption in a process. But modern protections mean you can't just inject shell code and jump to it anymore. So most modern exploits that take this approach use return-oriented programming, where you recombine existing snippets of code in the program to accomplish whatever it is you're trying to do. I made some bad diagrams to explain this. On the left is the stack as we expect it to be in normal operating conditions. The middle is the stack when there's a ROP payload that fully resides on the stack that is executing. And on the right, we have a ROP payload that uses a stack pivot, where the stack pointer is changed to point to the heap or wherever else the full ROP chain is. So BPF seems promising for this. We can instrument the kernel safely. CORI means we have a much simpler way of building and distributing whatever we wind up with as compared to building for a dizzying array of kernels if we used a kernel module approach. The send signal helper means we have enforcement, so we can kill a process instead of just alerting about it. And the situation of a stack pivot should be simple enough that we can detect it within BPF program restrictions. So what design did we wind up running with? Well, the situation we're trying to detect is that some userland program gets exploited. The stack pointer gets updated to no longer point at the stack. And at some point, it calls syscalls like execve to do something malicious. So if we can track every task's legitimate stack where it's supposed to be, attached to important syscalls like execve, and when those syscalls are hit by userland programs, check that the stack pointer still is pointing into the stack, we should be able to detect this and kill the process when it happens. But there's some issues here. On Windows, this is easy because the thread information block gives you this information, and you can just look at the stack base and stack limit fields to determine where the stack is. But Linux doesn't really closely track the stack quite like that, and doesn't even really have a well-defined notion of where a userland program stack is supposed to be. So we have to do some homework. The three cases we saw in practice broke down like this. The first one we called the system stack. Every process has this. The initial thread in a thread group is given the stack by the kernel, and the kernel manages it, grows it, and things like that, and saves the initial address of it in a kernel data structure. So this is pretty easy. We can just look up what VMA backs that address, and then check that the stack pointer still is in that VMA. The second case is for multi-threaded programs. To create a thread in Linux, you call the clone or the clone3 syscall, and when you're creating a new thread, you need to provide a new SP parameter that tells the kernel where the stack pointer is going to be starting off for this new thread. But the kernel doesn't manage that memory for you at all. It's all up to you, the user, which in practice means that a library or framework that you're using is doing it for you. In the case of pthreads, it just allocates some fixed region of memory with mmap, and then uses that as the stack for that thread. So for this case, if we can catch these regions as the threads are started when they're first created, then we just can keep that information in a BPF map to look up later to see whether or not the stack pointer still is in the memory region, the region of memory it should be in. The third case is a bit tricky because Golang just kind of does its own thing. The user stacks are dynamically managed so they can grow, shrink, or be relocated, but they're allocated on the Go runtime heap, which is allocated using mmap hints. So for this case, our heuristic is just that we check the stack pointer for this hint format, and if it matches, we decide this looks like it's a Golang program and it's probably okay. So as far as like a top-down view of this design, the heart of it is kind of this tracked stack regions BPF map that we keep consistent using a few different BPF programs attached to like fork or the execve return. Other BPF programs are attached to things like execve, where they can check the stack pointer against both this BPF map and our other heuristics. And if it looks malicious, then we always send an alert up to user space, but optionally can also kill the process using BPF send signal. So for some light testing and benchmarking, here's how it seems to fare. We set up a simple Kubernetes cluster with 2 nodes, a worker node and a control node. We had traffic pointing to Nextcloud on this. We had an internal Docker registry. We had BusyBox and Phoenix Test Suite, and a container for our proof of concept, all running on this one worker. As far as benchmarks, so I think these are a bit representative. Apache responding to requests and compiling the Linux kernel saw 5 to 10% slowdown. Postgres was negligible, kind of surprisingly. But the worst case was the micro benchmark of creating threads, which was over twice as slow, or over 100% as slow, which I think speaks both to how lightweight creating threads is on Linux, but also to the fact that this proof of concept, we didn't optimize it at all, really. And it still had a lot of debug print statements in it. So my personal takeaway is that this 5 to 10% overhead for typical workloads can probably be brought down quite a bit. And I would call it like a worst case scenario. A bit more importantly to me, I wanted to make sure we had no false positives, because if we want to automatically kill processes that look like they're being exploited on a cluster, if we have any false positives, then we risk knocking over a cluster for typical benign behavior. As far as the breakdown, we had 13 days of light usage on this cluster, and mostly we saw events we considered okay, where it was either the system stack or the thread stack, and a close second of events that we decided were coming from a Golang application, which we're running Kubernetes, we're running traffic, that's expected. We had what we called ancient thread events, where a thread was running and started before we were loaded, so we currently didn't have a way to determine if it was legitimate or not. But most importantly to me, we had no false positives. So my final thoughts from this are that this can detect stack pivots. We did test this very early. Our test program just allocates a ROP chain on the heap, pivots the stack to it, and exploits itself, which is contrived, but it makes sure we can tell the difference between the stack and not the stack. Some false negatives. The one false negative this approach can't get around is that if an attacker pivots elsewhere in the stack, this isn't granular enough to detect that. You would need a different approach. The current implementation also has 2 holes that we can close. If an attacker can control an allocation, then they can make their shellcode look like it's coming from Golang. We can close this by implementing some research we'd already done on determining if a binary is a Golang binary or not. Secondly, if we don't currently have a good way to protect threads that exist before we do, but I think a trust on first use approach would handle this case pretty well. Besides that, my takeaway is that this approach can work, and it's very beneficial that it can be applied to systems as they are, as long as you have a heuristic that can capture the complexity of real-world software without being so complicated that the overhead is unreasonable, which I think speaks to the other big takeaway, which is that optimization is absolutely necessary for this to work, because blocking one exploit technique is not very impressive with this kind of overhead. You need to get it down significantly so that you can be blocking a wide array of exploit techniques and really be protected. So that's all I've got time for. I'm going to leave this slide up for a couple seconds so that y'all have our emails if you'd like to contact us. Thank you for listening. I hope the rest of the conference is great.